hardest thing for you guys to do, especially when you're training, is to get your heads off of your devices and to start looking outside and away from blood vessels and patients and starting doing something that's different. And one of the most fun things to do is to do something that's uncomfortable. And we bring that to you here. We bring the uncomfort to you, and discomfort. And that is in this Innovator Series. And the first person I was told to come and visit when I got here, when I was getting recruited out here last year, was Francisco Valero-Cuevas by my friend Yoki Matsuoka, who co-founded Nest. She said, you got to see this guy. He's like world class, the best roboticist I know. So Francisco graduated from Swarthmore College. After that, he went to Stanford. After getting his ticket punched there, he came down here where now he's a professor in biomechanical engineering. He runs the Brain Body Dynamics Lab, which is the spectacular place. He's doing upper and lower extremity robotics par excellence, and I can't wait to hear what he has to say, whether it's with or without prompts. By the way, if you guys want to look up something while if you're on your devices, last year he was the commencement speaker at his undergraduate at Swarthmore.
Yeah,
that was freaking awesome. Yeah, you guys got to watch that. It was like a Steve Jobsian kind of commencement address. Francisco Valero-Cuevas.
Thank you so much, David. I really appreciate this kind introduction.
Yeah.
Actually, from Stanford, I went to Cornell, where I
forgot about that, man.
Yeah, so I was.
Ithaca.
Yeah, I was in Ithaca. I was tenured. I was tenured at Cornell in mechanical and aerospace, where this is normal. Out here, this is not normal. Actually, I was tenured at Cornell, where the medical center is in New York City, and we were over in Ithaca. And so when anybody tells me, oh, the UPC is so far away, you will get zero. In fact, negative pity from me. It's like, what are you talking about? I did this at Cornell where I had to like drive 5 hours or fly, and here we are neighbors, essentially. So let's use this. I think my main plea to you is to look beyond this campus. And so I'm starting other synergies. One of the things that I was talking to Yogi Mataru about, and to Yanis Yortsos, the Dean of Engineering, is to have a place where engineers are in contact with you as clinicians, where we have master's students who have the skill and are looking for content. So let me talk a little bit from the marketing side of things. You guys have content. We have skills. For any idea that you come up with, we can find 1 or 2 master students who will make it a reality. And they'll do 2 things. They'll offload your brain and your time, because you don't have time for that. But it will also expand your horizons. And for them, it's the same thing. You know, we love coding, we know all this stuff, but then we actually solve real world problems. So about Swarthmore, that was a great honor and privilege, where I was given an honorary doctorate in biology, of all things. And so why biology? From the beginning, I have a confession to make. I wanted to go into medical school when I was in high school. But I liked math too much. And so I had to make a decision. At the time, you know, the world wasn't as interconnected across fields as it is today. So then I had to make a decision. Later on, I realized that through the efforts of many people in academia, that was a false choice. So I tell you the same thing now. It is a false choice that you are clinicians only. Clinicians only, right? You are many other things, and in this world, you can actually dislocate those paradigms and actually do whatever it is that you want to do, where you can make the biggest contribution. And we're here to help, actually. So let me tell you a little bit about what motivates me and why. My main interest, ever since I was young, was like, oh my God, look at these drawings by Da Vinci, whom you could call a clinician in some circles, or at least an anatomist. He saw organisms as machines. Because in the drawings that he makes, he uses even ropes at times to depict muscular tendons and such. So I said, like, wow, this is really cool. Organisms are machines, and so you can go the clinical side, you can go the engineering side, but at the end of the day, this idea that organisms are machines is fascinating. Now, I'll tell you a secret. This is what puts us engineers, makes us very nervous. In fact, it depresses us every day. We have super fast computers, amazing materials. We have algorithms coming out of our ears. We have techniques, we have CAD. And we still are envious of the ability that organisms have, even in the simplest types of organisms, like, for example, a mouse or a cat, right? So if you look at how organisms are put together, they have slow, noisy, and stochastic signals traveling. They have slow and nonlinear actuators, or muscles. They are fragile. I mean, you can like hit yourself and cut yourself. You can really injure yourself very easily. Yet, they work better than anything that we can throw in comparison to organisms. Now, I'm no spring chicken, right? But not so long ago, roboticists, we were saying, look, if only I had a faster computer, my robot would just walk out of the room. It would be amazing. And we would used to, we used to sleep well at night by saying to ourselves, if only I had faster computers. Even 15 years after that, where are we? Do you have fast computers? Well, that's not a problem, right? And we still cannot get that to work. In fact, the question is, where have we as engineers missed the boat? Why are we not creating systems that are even approaching what we see in nature? And so the question is, why? Where is that issue? So that is actually the central question of my lab. And that's why it's called the Brain-Body Dynamics Lab. So I want to build better robots. I have another confession to make. I'm like a shapeshifter. So if I can talk to you, and we could talk shop, we could talk clinical stuff and anatomy and this and that. I can go to neuroscience meetings and talk brain and neuroscience and this and that. Or I can go to engineering meetings and talk robotics and dynamical systems and differential equations. But the only reason I do that, what drives me to do that, is to be able to understand how is your knowledge, what you know, going to help me in the goals that we have to combine fields. And for me to do that, I have to be a shapeshifter. Anthropologists call this immersion into a culture. So I actually see that the biggest obstacles to scientific and clinical progress is not technology, is not knowledge, is not anything like that. It's actually a sociological problem. It's an anthropologic problem. Why? Because in any field that you enter, you have to walk like a duck, talk like a duck, be accepted, be promoted, be successful, and you right into the sunset, right? You must do that. If you go into any field and you're not doing that, then you're not going to be a member of that sociological group. That's why you guys enjoy the white coat, right? I have a white coat, sometimes I wear it, I didn't bring it today, but that is a marker that immediately identifies you with this community. So what my job is actually come to your community, learn from you, go to another community, and then talk like an engineer, walk like an engineer, talk a differential equation, see what their knowledge is, and then try to bring these worlds together. That's why you have a jewel of a mentor here, because he also does the same thing. He also wants to understand what else is out there, and that was actually one of the ways in which I can interpret his comment. It's good. You must become the best clinician possible. Why? Because we, outside of your community, we depend on you to be that. But at the same time, you want to be something else. You want to reach out and learn something different. And this is where this interaction happens. So what made me into into this, I would say, is my interest in understanding how brains control bodies, how mathematics allows us to understand this. And the only way I can solve these problems is by surrounding this brain-body interaction from every direction I can think of, and collaborating with as many people as I can, because these are complicated problems. So one way to say this is that engineers from the times of Borelli and Da Vinci, we saw organisms and we saw, wow, I want to make a bird, I want to make a horse, I want to make a machine that does this. So we went away with that inspiration, and then we developed the mathematics that allows us to understand how that is. Now, why mathematics? Because Galileo Galilei actually said it in his preface to his famous book, where he said, the book of nature, I'm saying it in modern words, the book of nature is an open book, and mathematics is the language. So he was saying, in 1640, he was saying, look, there's all this stuff in art and biology and nature, philosophy as they used to call it. But actually, if I know math, it becomes an open book. So we as engineers went away, we developed the mathematics that brings you robots, cars, airplanes on all of that. So I went and I learned those mathematics, so that my PhD and undergraduate and master's degrees, they're all in engineering, mechanical engineering. And now I'm returning the favor. I'm reflecting these mathematics, and I'm looking at biological problems, and I can ask, how can I get clarity here? Why? Because guilty as charged. I agree with Galileo. Mathematics is a language that is very powerful. And actually, this has made me reflect. Back in high school, you know, when your formative years, you know, and you had some smart friends, right? And those smart friends were either of two flavors. I realized that friends come in two flavors. Those who like math and those who run away from math. And if you like math, you would culturally be driven into this and that and the other field. If you ran away from math, you would go into biology and medicine and art and literature, right? And that's silly, because it's a failure of the educational system to let you see the beauty of math. And I see math as the place where truth and beauty intersect. I know of no other place where truth and beauty come together as they do in math. But how can we convey this to people who were taught math in ways that just make them allergic, right? So never fear. You don't necessarily need to get into the math, but you can work with us. Especially there's a community of us who know the math and stuff, but we want to listen. We want to understand what you think is a problem. And here we're back to sociology. So the idea is, if you tell an engineer there is this situation, the engineer will come up with a solution, right? If you tell a clinician there's this situation, the clinician will come up with a solution. Now, if you pay attention carefully, what the nature of the problem is and what the definition of a successful solution differ widely between one and the other culture. So to an engineer, if it runs well, if it uses low battery, if it's robust, like you can connect to it in any place you go to try to give a talk, that's the solution, right? Whereas to a clinician, perhaps is quality of life. Does this person now have the ability to get up in the middle of the night and go to the bathroom without falling? Maybe that is a solution in the clinical domain. And so to me, what's very interesting is this interplay that can only be called like almost a, it's a very active debate of how to arrive at a reasonable compromise that helps the client. Who's the client here? Who is the client? Well, it changes. Like in business development, you're always asked, who's the client and who's the customer, right? Who's the customer is who benefits from this. Who's the client is who's paying you, right? And throughout your careers, you will realize that there's a client and a customer, and the situation changes. But what's most important is to be able to stand back and then ask the question, who really is, what is the problem, what is a solution, who's the client, who's the customer, who can help me do this? So, as engineers, I mean, we can publish a lot of papers and they will nicely decorate some shelf. Actually, not even, now it's all PDFs, so nicely fill a directory, right? But is that actually going to change the world? And that's one of the things I really liked about biomedical engineering, that you can actually help people. So this is a long-winded way of saying that what I've been trying to do all along is combine these two cultures, combine these two worlds, combine these two world views, combine these two value systems to do good science, right? So that's kind of why it's called the Brain Body Dynamics Lab. And I could tell you about how we do neuroimaging, we do neurophysiology, we do robotics, we do modeling, we do all sorts of things. In fact, this week I just found out this morning that we have an article about taking a robot leg, that is a tendon-driven leg, and use motor babbling, just like children do, to have limited experience, just like we do, because there's a risk to us doing a lot of training, right? You can hurt yourself, you're wasting time. Somebody else is already getting your lunch while you're trying to perfect your gait, right? Or maybe there's a predator-prey interaction, like you're born like a calf and you fall out of your mother's and then you have to start walking. So we replicated that, and we can actually teach a leg to learn a style of walking, a motor habit within 5 minutes. Real-time 5 minutes. The current state of the art is to give it 10 years of accelerated exposure to its body and then take your first step. We do it within 10 minutes. And this actually the cover article for Nature Machine Intelligence that's going to come out next month, right? And so the question is, how is it that I can produce work that is pushing the envelope of say, artificial intelligence? Because I'm competing against Google, I'm competing against DeepMind, I'm competing against Amazon and artificial intelligence, and we can come up with something that is better than what they're doing in some domain, right? Well, because for these and other projects, I've always insisted to my students, let's do a project, but let's not do what is convenient. Let's ask the question, let's ask the hard question. Why do we need to have 10,000 repetitions of some task to even begin to learn it? That makes zero sense, because in biology, that's not how it works. So what I want to do is I want to reverse engineer and recapitulate the evolutionary process. How is it that the properties of the body collaborate with the properties of the nervous system to give us the function that we see? And in fact, what's interesting about biological systems is not that they work so well, but that they work at all. Let me say this differently. Imagine you have an organism that has dumb neurons that are trying to talk to each other, that are slow, noisy, probabilistic. They have no actual knowledge. All they are these integrate and fire little units that are connected through slow nerves to sluggish muscles that are pulling on viscoelastic strings. How do they even work at all? So, let alone that they work so well. How do they work at all? And in fact, I see evolutionary biology operating in this very difficult environment where Newton and Darwin are both relentless and unforgiving arbiters. What do you mean by Newton and Darwin? Well, the origin of the nervous system was to interact with the physics of the world. We used to be plants, or we used to be single-cell organisms just floating around. And then all of a sudden there was this development where like, oh, maybe I can control my position in fluid. Maybe I can actually want to go towards food or towards mate or wait for noxious things. And that's actually the birth of the nervous system. How do you deal with the physics of the world? That's one thing. And the physics are not forgiving. You either fall off the cliff or you don't. You either make it to the surface and get sunlight or you don't. And that's where Darwin comes in. Darwin says, whatever you do, if you're not doing it as well or better than your peers, you're going to be toast. And so this is how biology evolved. And so to me, that's a fascinating question. And in the context of the clinic, I want to understand the mechanisms that produce disability. And also, what can we do about it? And in particular, there is this kind of astonishing hypothesis, and I'll tell you it, that the properties of the nervous system and the nerves and the muscles, it's a little disturbing when people are not looking at me, when they're looking at their phones. Hello. Yeah, just give me 10 minutes of your time, and then you can answer your text. Let's just give me 5 minutes. I do this in my undergraduate classes too, and graduate classes as well.
It's been a while since undergrad.
Yeah, so maybe people don't remember. Now, actually, it's a big issue. This fragmentation of attention is horrible. It's killing us. It's an important problem in science. But be that as it may. So what I was saying is this hypothesis is that the presentation of a clinical condition, the disability, is a result of the tissues and mechanisms that produce behavior. Let me say it differently. Imagine you have someone with Parkinson's or someone with tremor. Tremor probably arises because of the unintended consequences of how the nervous system is wired to muscles. Makes sense, right? But if you look at the Parkinson's literature, people are saying, well, if I have a mathematical model of the basal ganglia and its interaction with the cerebellum and the motor cortices and how they're projecting through muscles, then tremor is nothing other than some generator of a frequency of oscillation that then gets propagated and I get my tremulous behavior. That's one way to look at it. The other way to look at it is that there is no such generator of an oscillation, but that the oscillation emerges as an unintended consequence when the system is out of equilibrium. So that actually to understand disability and how to deal with it, you have to understand the mechanisms that produce it. Not just a high-level idea of, well, somebody's generating an oscillation, but why? Now, if we talk about this a little bit in the context of say, diabetic foot or neuropathies, yes?
Sorry,
And I don't know how much time I have.
Oh, well, we're right up against it, but that's okay. Because this is, go ahead.
Yeah, yes, please.
So if we can be a little bit more interactive, rather than imagining and going on to another problem, I have a patient
Yes.
who is completely paralyzed after thoracoabdominal aortic aneurysm repair due to spinal cord ischemia. We have no way of
spinal
helping
cord
this.
injury or?
Spinal cord ischemia, infarct, as a consequence of thoracoabdominal aortic aneurysm repair. I've been searching all over the place, trying to find somebody who can help him, either with a smart prosthetic, neuroregenerative procedures, anything investigational, experimental, beyond what we can do essentially is nothing. This is a real patient that comes to my clinic every year, every 6 months, and I see this 47-year-old guy just wasting away.
And so the problem is that he has essentially paralysis.
He has complete paralysis.
Okay.
So is there anything that we can offer him at this moment, or how do we make something happen that we can start researching to help this guy in concrete ways?
Is he flaccid or spastic?
Flaccid.
Okay. So with flaccidity in these contexts, probably the main issue are, pressure source. That is kind of his biggest problem.
He
risk,
actually,
right?
so he has been completely paralyzed like this for about a year and a half.
How does he manage? How does he manage the
So
pressure
he's
source?
a young guy. So Vinay, Daryl Vinay is his name. He's a young guy, so otherwise is healthy guy. So he actually does a great job using his upper extremity, using his wheelchair, and relieving pressures.
But I'll tell you that
I want
even
him to
yeah.
walk again using something or some robotic something.
Yes.
But how far are we from being able to offer him anything?
Well,
and can you point me in some direction that he would be willing to enroll in any kind of? And what does a regulatory aspect of and the university look like as far as getting him to someone who can help him?
So one of the things, so I'm familiar with the rehab robotics world, and I'm familiar with for example, the rehabilitation for spinal cord injury and things like that. One of the things that makes me so excited about this paper we're publishing in Nature Machine Intelligence is that my dream, and I cannot offer it tomorrow, but if we find a way to fund this, let's do it, right? Imagine you have an exoskeleton, right? And there are exoskeletons out there. Have you seen exoskeletons in practice? Have you
No,
seen them
but
work?
this will be a
So-
perfect
so-
guy for
so-
something
so-
like this.
But so the other ranch. We'll talk in a minute because at Rancho I'm going to see it this afternoon.
I've been talking to Charles Liu.
and-
or
and-
Yeah, Charles
and-
would
and-
know, yeah.
and-
Okay, and I've been talking to everybody I know, neurologists, urologists, like colorectal surgeons, and nobody has come to concrete, like, specific solution for him.
So-
So yet, I talk to all these people, and I'm a little bit frustrated because I talk to all these people, and they know about all these things. That's great. Yet, Mr. Vinay is paralyzed in his wheelchair, and nothing is being done.
This is exactly the kind of conversation that I find most useful.
Yeah.
Because if you tell me what you see as a solution, I can try and see if I know of a way to provide that. So what would, in your dreams, if you had a magic wand, what would you provide him?
Anything beyond standard of care for somebody like him, which is essentially wheelchair and turning. And
Wheelchair
intermittent
and?
and turning around, just the spinal cord rehab at this point, for him, a year and a half out from his paralysis and rupture, is essentially, okay, here's a wheelchair, and here's some prosthetic things, and here's some braces for you
To
for live your
palliative,
life,
it's
which is
really-
not proactive for this 47-year-old guy.
So then the question I would ask here is walking around a necessary and realistic goal?
You tell me what's out there.
Or is quality of life the goal?
Both.
Both. Now,
Right? I mean, walking around, being able to walk around beyond.
so
wheelchair.
is mobility necessary? And the reason I say this is because there is this community that is saying, what if mobility is a nice thing, but actually we're imposing on the disabled our version of normal? What if for someone like him, the best thing to do is to have like some sort of virtual reality environment where he's out in the world? Because lack of mobility is a huge problem in the elderly. Actually, I think the best thing about Uber and Lyft is not that they can get you from your lunch to your office quickly. I think it gives the elderly freedom and participation in the community. And we actually had a project with Carol D. Winstein and Rancho Los Amigos, optimizing participation through technology. I think the best thing about Uber is that my mother can go see her friends without having to like drive, without having to find a way to. So then this is a very, let's do lunch, as they say. Because I want to understand, because we need to brainstorm what is better for our client.
Yeah, no, I think you're putting it in a completely different framework, and he also happens to be a computer engineer.
So
the other thing is, so right now with BC, with brain-computer interfaces, kind of the bleeding edge, or with exoskeletons,
Yeah.
one of the big problems for practical use still, battery power.
Which we are actually solving. It's no.
because
Can he be a subject to all your testing?
I mean, like,
But what about, but what about, hey, but what about a better, but you guys ought to talk about, like, what about a better,
Prototype testing.
what about a better wheelchair?
a better wheelchair.
So-
Or for under $1,000, I can get him a killer VR set, head mounted.
Yes,
He would be interactive.
anything.
A friend of mine, for example, is at Johns Hopkins for stroke patients. He says, why don't we give them the swimming with dolphins experience? With whatever mobility you have,
I want that.
you could be swimming with dolphins. Yeah, and in fact,
$100,000, you say?
and in fact, when you think about it, we're so happy in our skins because we think that this is all there is. So cognitively, because of cognitive dissonance, I'm not depressed that I do not fly. I would like that I don't have wings. Why am I not depressed about that? Well, because so we have this normal, right? So what is the new normal for people with disabilities? What should it be? And shouldn't they be in control of that? Given that they're the ones with a disability and every person is different, how can we help them? Because if I'm an engineer, which I am, and you tell me, oh, couldn't we create an exoskeleton that have him walk away and play basketball with his kids again? That would be lovely, but maybe I'm imposing my value system on this person. And then there's the issue of cost, benefit, timeline.
So I understand that point. But like, for somebody like him, who wasn't born with this, it's not our value system, it's his value system as opposed as a year and a half ago, and his life
Yes, and that's
drastically changed.
And that's
so,
why depression is a big deal in disability,
Yeah.
right? So
And
there
I've
is a,
seen it.
I mean, look for all of our patients.
Yeah.
I would wager that probably 70%.
yeah.
It sounds crazy, but I think
That's
probably about
not-
70% of our patients are clinically.
Yeah, and actually, I worked at my PhD was done at the Palo Alto VA in the spinal cord injury clinic, where I worked with Rod Hens developing tendon transfers and things like that. In fact, we have a patent that's funded by DoD, and we're wanting to get out to the world. I don't know whose coffee this is, but may I have it?
Sure.
Yes.
Yeah.
So imagine that you do a tendon transfer that flexes all of the fingers by using a motor, say brachioradialis or extensor carpi radialis or something, and it just flexes everything at the same time. Problem is, if I try to grab this cup that's irregularly shaped, whenever the first finger stops, they all stop. And then you cannot have functional grasp. So then we invented this thing. It's a little mechanism that you implant. It's patented, and we're now trying to find an FDA path for it that actually adapts automatically, passively, and perfectly to any irregularly shaped object. So if you're picking this up and you have that tendon transfer, you can actually pick it up like this, you can pick it up like that, you can pick it up like that. Doesn't matter because it adapts by itself. So this is again the brain-body coevolution. So whereas the current transfers, if you don't get it the right way, then everything stops. Let's do lunch. What I wanted to show you is this, which is another invention that is now a company, a startup company that's struggling to survive. And what we're doing is we can quantify neuropathies. We can quantify return to sport. We can quantify low back pain. We can quantify titration of deep brain stimulation in Parkinson's disease. And what it is, I mean, I don't have the video, but I can show you this thing where what you do is you say, turns green, and with your foot you press down. Come try it later on. The more you press down, the more unstable it gets. So the further you can go tells me the quality of sensory motor processing that you have. Because nowadays, and I was actually I had my physical and say, oh yeah, tomorrow I'm going to talk to the cardiovascular, the vascular surgeons and this and that for, say, diabetic foot. And he says, yeah, well, I send them to get to the neurologist to get their nerve conduction study. Which is true, which also happens for entrapment syndromes and stuff like that. But if I were to tell you that the delay from thinking to do something to producing a force to making a decision about how to adjust it, if I were to tell you that that delay is about 120 milliseconds, what does it matter that I have a 5 or 10 millisecond delay in the cable? Why is that even informative of the disability? Because the brain is plastic, so if my conduction becomes slower, I'm going to adapt. I'm going to do something else. The brain is going to start listening to other sensors. It's going to do what's called sensory fusion. So with this, we can actually begin to quantify. I can give you a number and then compare that patient to themselves in the past and then tell you where they are, or to everyone else of the same age, sex, condition, medication, surgery. Another thing that we can do is if you have the insensate foot, I can pick that up. I can tell you in practice how insensate, how lack of sensation is affecting their behavior. I mean, you could do Weinstein's, you can do the swipes, right? But what's that going to tell you? It doesn't tell you how the person is doing this. So this is particularly important, like where if you want to do a surgery to repair a defect and the person really is very low in their ability to regulate their forces, then you can do the surgery, but they're going to tear it up because it's too far gone. Or maybe you know that this is a good candidate for a more extensive reconstruction because they found a way to control their interaction with the floor. So it opens up a variety of questions, but the most important thing is that I come to you not with a hammer that's supposed to work for every nail. I want to know from you, just like they did now, what matters to your clients and why? What is the real question? What is going to help provide better care and make you famous and all that stuff along the way, right? Why not? Publish and get funded and be recognized, and like we've talked, you're here not because we want to make you participants in this wonderful field of vascular surgery. You're here because we want to make you leaders. Why bother training participants? We must train leaders. And for that, we must challenge you, and that will be uncomfortable for you and for us, right? But that's why you're here, and then you're in an incredible environment to be able to do this. So, again, I'm an engineer. I do clinical stuff when I find the collaborators interested in these things, so I think I should wrap up.
Well, listen, here's, you always say that engineers solve yesterday's problems tomorrow if they're left by themselves.
Yeah.
But I think doctors sometimes do the same thing. When we get stuff together, that's when kind of the magic happens.
Yes.
So here's to some magic happening. That was really awesome, man.
Well, thank you.